Engineering. So this is my great pleasure to have this lecture together with our future of membrane people in Korea. So today, I'd like to talk about resource recovery for 1 hour. So last year, I mentioned about the how to design the seawater reverse osmosis design very briefly. And then this year, the Professor Nam, he asked me to change a little bit for brine mining for resource recovery, which is one of the hot topics research. So my contents are seawater constituents. I'm sure that everybody knows seawater, but not many people know what's the inside, exactly concentration and different elements. So we need to know more detailed constituents. So desalination, how it works and the processes. And we need to also know a little bit of chemistry. So I'm not sure that I can see from this webinar, around 25 people are here. I cannot see the lecture room. So how many people are in the lecture room? So they have a different background. Somebody from chemistry, somebody from civil engineering, environmental engineering, chemical engineering, mechanical engineering. Some people are maybe environmental scientists. So we have a very different multidisciplinary background. So it's very difficult to satisfy everybody's expectation from 1 hour lectures. So this is overall concept rather than too much specific brine mining. So just you capturing what's going on in the brine mining, so you can decide yourself. So if you're interested more detailed information, so please contact me, or so you can digging out your brine mining research in the technical papers. Because we will share how we can achieve this brine mining. So at the end of this presentation, I like to have a little bit of a discussion. If you have any idea what could be the future of the brine mining, so this could be the next research and commercialization opportunity for desalination or not. So we can have a little bit of discussion. Any questions so far for the contents? So my voice, everything is okay to follow up this class? So no response, so which means everything is okay. Yeah. So let me start. So seawater is a reliable water and food, mineral, energy resources. So think about the seawater can produce the wave renewable energy, tidal, and we can have hydrogen production from seawater desalination. Also, we have a lot of wind farm near seawater area. And we have food, like every day you enjoy fish, like sushi, sashimi. So seawater provides a lot of nice food, protein to the people. And water, we have seawater desalination, which is very important to everybody. So seawater desalination is becoming more and more popular because everybody want to stay near the ocean because they can enjoy and entertain the beaches and the water swimming, as well as we need to look at the minerals. So sea salt, seawater, the water contains 96.5%. And sea salt, we have chloride 19.25 gram per liter, 55%. and sodium 30.6%, around 10.7 gram per liter. Also sulfate, this is 7.7%, calcium, potassium, magnesium, also minor constituents. So we have a lot of lithium inside seawater concentration around 0.2 milligram per liter. Also rubidium, 0.2 milligram per liter concentration. Also we have uranium, cesium, some of the minor constituents, which are very valuable material, can be obtained from seawater. So let's think about how we can utilize this seawater source for the seawater brine mining. So we need to look at first how the desalination is growing nowadays. So you can see the world mapping for desalination. United States, Saudi Arabia is the largest desalination plant at this moment. Mostly the Middle East country, they have a lot of desalination plant. Also Australia. In Korea, they have one large desalination plant, which is Daesan desalination plant, 150,000 cubic meters per day. And Korea also, there are a lot of islands. They rely on the seawater desalination using RO for distillation process. So more than 100,000 desalination plants you have in Korea as well. But difference is you have not tasted the desalination plant much because Korea has a very major 4 rivers and enough fresh water so that it seems you don't need a desalination plant, but whether you have experienced K-Water has built on this desalination plant. Also in the future, the Busan or some of the coastal area, they would have also desalination plant, not only in terms of water quantity as well as water quality would be the one of the reasons desalination is one of the very fresh water resources. And keep growing from last 400 years. So you can see the what's the growth rate of the BWRO and SWRO and summer desalination plant. So you can see the summer desalination plant was dominated before 1980. However, the SWRO has been growing because of the more energy efficient process. So you can see the summer process is very steady, but the SWRO is keep growing. So you can see the SWRO, BWRO, you have almost $6,000 million, which means $6 billion capital expenditure. So this is only capital expenditure, $6 billion. And the OPEX operation and maintenance, when an expenditure is almost double every year. So $12 billion. So altogether, desalination market is every year $20 billion. To almost you have this $20,000 million of the market for desalination. So if you see the very latest information in terms of, let me remove this one. Global cumulative contracted and installed capacity up to last year. So you can see that desalination is keep growing. At the same time, the reuse, water reuse was very significantly growing the market because still desalination is very much limited in the coastal line, but inland area, so you need water reuse. The seawater reuse or wastewater reuse, seawater desalination have been increased for overall capacity. So this is last year, 260 million cubic meter per day. And seawater desalination was 120 billion cubic meter per day last year. So if you look at the history of the SWRO, initially distillation was dominated for the desalination. And then 1970, so seawater reverse osmosis membrane was discovered. After that, it took almost 2000 to catch up with this distillation process. So even though technology was discovered 1960s and then commercialized the SWRO 1970, however, to take over this desalination process, so it took almost 30 years to replace with the reverse osmosis. So our membrane has been dominant since the 2000, and this is the first our innovation of the SWRO. And then the U.S. Navy, they discovered the pressure exchanger. So this pressure exchanger decreased the overall 10 kilowatt hour per cubic meter SWRO or distillation, almost half, 4 kilowatt hour per cubic meter of the desalinated water. So this second innovation of SWRO was SWRO is this pressure exchanger. So it has been increased the SWRO from 2000, and then now is more this SWRO has been dominate the market for seawater desalination. So what's the next step? So we have had two innovation, SWRO, membrane and pressure exchanger, almost this time. And now is we need to look at some more energy reduction after two innovative idea. So that could be something we can think about energy. So energy is almost you need 3.9 kilowatt hour per cubic meter. So intake 0.2 and pretreatment 0.4. RO is largest energy consumption 2.8 kilowatt, and production delivery is 0.3, and discharge other is around 0.2 kilowatt hour per cubic meter. So SWRO membrane was a very critical development for the reducing this energy consumption from 10 to 2.8 kilowatt hour. But still, this is a very high energy consumption. So people like to reduce further. So if you think about energy in terms of in kilowatt hours, so seawater desalination power energy, the most dominant for the operating cost. So 1 kilowatt hours in Australia, we cost around $0.29, which means around 300, almost 250 Korean won. And this one, we need desalination plant 4 kilowatt hour per cubic meter. So when you produce the almost 1 cubic meter of desalinated water, so you need around $1.2 Australian dollar to consume in your energy. So if you look at Sydney desalination plant currently produced 250,000 cubic meters per day. So how much it cost is around $290,000 per day, so which means almost $300,000 you need to support your energy consumption. So we need to have another more cost-effective desalination. The first, second, now is the third generation of desalination after our innovation. So brine mining can be a next third innovation for SWRO. That could be the we need to investigate further. So that's the one of these lectures. After this class, you can think about how this will happen in the future of the brine mining and seawater desalination plant. In Australia, we have a 6 desalination plant, and then mostly they utilize the wind farm renewable energy. And currently, most of them are under operation, but some of them, when you have a lot of the dam water, so they have a standby mode. So Victoria, not really operating. Adelaide around 20% operation, and Gold Coast also they have enough dam water, so less than 10%. But Sydney, Perth, Southern seawater desalination plant are fully operational, and then Sydney desalination plant also planning to increase the double size of the desalination plant next couple of years. Also, they like to have a more desalination plant with the middle-sized city, like Newcastle, Wollongong, Cairns, Townsville. So there are a lot of the middle size of the city in Australia, so that we will have a more desalination plant to make sure that the safe water resource from seawater. So this is the Sydney desalination plant water process, chlorination, and then iron chloride, pH adjustment, and dual media filter. Because you need anti-scalant to reduce the inorganic scaling for reverse osmosis, and dechlorination to protect the polyamide membrane. And you need a post-treatment after RO, and product water fluorination, chlorination, and supply to water distribution. So at this moment, this desalinated water combined with the dam water, so almost 15% of the desalinated with mixed with the dam water. So it supplies the Sydney area. So when you come to Sydney next time, already this water in the city is mixed with the desalinated water 50%, and you would taste the desalinated water mixed with the fresh water. So brine mining from the seawater, you can think about what kind of material we can recover. So you can see the seawater brine mining different element contains. So we have a multivalent ions and monovalent ions. So you can easily first precipitate calcium precipitate with calcium carbonate using sodium carbonate. And then you can have a multivalent separation channel, monovalent separation channel. So you can separate using nanofiltration. The multivalent goes to this stream, and the monovalent goes to this stream. So multivalent with advanced membrane crystallization, you produce the magnesium hydroxide, which is one of the very important mineral, magnesium. Also, water can be extracted, and then you can have a further metal and extraction from the polyamide ion change membrane, selective membrane, and the 3D absorption module, ionic liquid material to capture this specific multivalent ion, indium and molybdenum and gallium. Also, if you see the monovalent ion, you can use advanced multi-effect distillation, and then you can concentrate factors 4 and produce water, and you can collect your mineral, which is rubidium and boron, also lithium, also some of the sodium hydroxide, using this kind of absorption or electrochemical processes. So this is the typical way of the brine mining you can achieve, but it's not easy to make this kind of process with cost-effective as well as the compact process. So that could be the next challenge, how we can effectively and recover our targeted ions. So we need to investigate more details. And this is the brine mining in terms of concentration in seawater, and this is the price for US dollar per kilogram. So you can see that a lot of concentration is very less than 1 ppm. So this is very low concentration. Also, this is the little bit high concentration side. So you can see what's the value of this material. Rubidium looks like one of the target material, which is around $10,000 for 1 kilogram. And then concentration is reasonable, around 0.2 milligram per liter. Also lithium carbonate and $10, bromine and $10, magnesium $10. Magnesium has a very high concentration, more than 1,000 milligram per liter. Bromine is around 100 milligram per liter. So if you see these 4 elements, rubidium, lithium, bromine, magnesium, so that could be a very good opportunity. We can extract the valuable material from seawater. Additionally, you can see the boron, strontium, potassium, calcium, sodium, magnesium, and different element also you can extract, which is also not a bad value. Also, you have $1 per kilogram because they have a very high concentration, so that you can possibly make a return on investment. So brine mining, this material can be recovered cost effectively. So that would be the research items we can think about how we can improve the overall brine mining from seawater. And this is one of the commercially active brine mining from Neom City in Saudi Arabia. So they are now creating the largest desalination plant for the Neom City, the 1 million cubic meter per day, which is the world's largest desalination plant. Get the seawater from Red Sea and get the pretreatment, cartridge filter, and nanofiltration. So you can separate monovalent ion, divalent ion. So divalent ion goes to some brine management. Also, we have a monovalent ion mixed together to have this brine mining processes. And the rest of process is very much similar in general desalination processes. And this brine mining, after you collect your salt, go for the membrane brine concentrator. The membrane brine concentrator has been developed for the last couple of decades. So you improve the high pressure, like you can increase up to 100 to 150 bar, which can further concentrate your salt, so that this is possible. SWRO can use as a brine membrane concentrator with the high concentrated pressure application. So after that, you can increase around 150 to 200 grams per liter of almost 20% of the salt goes to crystallizer, which is the distillation process. And then you can recover sodium chloride, 25%, and then salt as a dry salt. Crystal sodium chloride can be used in chemical, pharmaceutical industries. Also, you can collect your bromine production. The bromine concentration can reach to almost 3,600 tons per day. So if you remember, bromine concentration in seawater was 100 milligram per liter. And then after 1 million cubic meter per day treatment, it comes to 3,600 tons per day, and which means 1 kilogram of bromine is almost $10. So you can get almost $36,000 for bromine with this process. Also, you will get the sodium chloride crystal. At the same time, rubidium, lithium, and some of the low concentration monovalent ion can be obtained from this process. So the New York City, okay, they are actively developing this one, and pilot is currently demonstrating in the seawater desalination plant, and then in the future, yeah, they are making this full scale of the resource recovery from SWRO brine. So you need to look at a little bit of chemistry to recover your targeted ions and resources. So let's have a very brief water chemistry in seawater. So if you see the seawater comes from intake, and seawater contains a lot of inorganic carbons, which is CO2 or bicarbonate and carbonate. So you can see the equilibrium of inorganic carbon. So seawater pH is around 8. So 100, 200 years ago, seawater pH was 8.2. So now it's decreased around 0.2 because of CO2. So CO2 increased, then you have more CO2 concentration. That's the reason why pH is keep decreasing. So if you have a more pH 8 or more than 8.2, so you have a more carbonate, bicarbonate, which is very important for coral or some of the calcium carbonate material related animal in seawater, such as crabs, lobsters. So all their skin is made by the calcium carbonate or calcium material, so that you need to have enough pH. Otherwise, the next couple of decades, you would not have any more crabs or lobsters because of this CO2 and then pH relationship in seawater. So this will impact the overall your inorganic scaling in the reverse osmosis, the calcium carbonate on the outer membrane. So you have this crystal, and this is calcium sulfate. So you can have different types of your scaling on the membrane, and then magnesium carbonate. So anti-scalant are needed to prevent this inorganic scaling. So people utilizing a lot of different material, but the SHMP or some EDTA or some of the acidic, like fatty acid organic compounds are utilized for anti-scalant. And this material is just dosed in this input area so that you can recover high water. And this is the dechlorination. As I mentioned, you need to dechlorinate just before reverse osmosis. So you need to chlorinate because of the bio impact. So all the process, biomedical filter, flocculation, pumping, and pipeline. So if you don't reduce the pH and the chlorinate, so you cannot operate because of a lot of the microorganism, algae, or some of the bio impact. So you need to put the chlorinate to kill all the bacteria. And then you need to dechlorinate because you need to protect the overall your polyamide oxidation process. So the chlorination can be processed with addition of the SBS. So you can use this SBS with chlorine, and then you can create just HCl. So you don't have any more active chlorine compound. So you can put SBS or granular activate carbon filter would be oxidizing the chlorine to ions. So that's the two process can be used, and then you can have also demineralized process. So after you concentrate your seawater, so you can have a post-treatment, and because this is too pure, which means you don't have buffer solution, will be very much easily contaminated, also easily damage your pipeline, and that's pumping as well. So that you need to have a good minerals, so low mineralized, high corrosion potential. Also, you have some of the minimum mineral requirement for your drinking water. The WHO recommend 10 milligram per liter of the magnesium, 30 milligram per liter of calcium. So you need to mineralize with CO2 to produce your carbonate with calcium carbonate, magnesium oxide, and then sodium carbonate, and then you can have a calcium chloride. Also, this material can be added to produce enough buffer solution in your desalinated water. Also good for your health condition, magnesium and calcium. And finally goes to fluoride, which is good for your teeth cavity protection, and chlorinate and discharge. So this is the basic chemistry you need to understand in seawater desalination. And from there, we need to collect the ions. All the compounds are already included in this basic chlorination. You have mineral addition as well as some of the pH adjustment, and you have some iron coagulant. So based on your pretreatment anti-scalant, so we need to look at the mining from the brine. So minerals from seawater, the ocean provide already 40% of the magnesium, because magnesium concentration is relatively high in seawater. Also, 1/3 of the world supply salt also comes from the sea. Like everybody utilize the salt. So where is your table salt? Some of them utilize the sea salt. Some of them use very purified sodium chloride. Some of them utilize the Himalaya pink salt, which is the very much algae combined pink color with the salt, which means this is Himalaya groundwater, and they have a different way of the salt. And then even you need to look at carefully your table salt. So where is your table salt? If you look at the table salt production area, every country you can see they have at least one or two very big table salt production line. So you can see there's so many the white this scale signature. You can see every country looks like they have at least one table salt production line, including the Australia in Melbourne, South Australia area. Also potassium. Potassium is good for pharmaceutical industry as well as the fertilizer, NPK. So you can see the fertilizer they produced from this sea area. And then magnesium, number 3, red color, magnesium production line. You can see a lot of the magnesium concentration extracted from seawater. Also bromine is collected from seawater. You can see where is the bromine concentration area. So even iodine. So already we utilized a lot from seawater salt. So how this process is working and how we can develop further. So that's our next mm, challenging, because already there are a lot of production line. They are already in the market, and we need to compete with the existing market with the seawater desalination plant. So we need to look at carefully how this process can be more effective when you combine with the seawater desalination plant. And then what could be the quality issue? As I mentioned, the chemistry of the seawater, we put the pH adjustment, the iron coagulant, and the escalant, and how this will impact for overall table salt. The quality issue. So that's all correlated in the future, so that we need to see how we can make sure that supply economy for salt production together with the seawater desalination, that will be a possible opportunity. We need to think carefully. So let's see the concentration versus precipitation. So you collect the seawater from your area. So you are very close from seawater in South Sea. So after this class, after maybe you finished on Saturday, last class in the afternoon, so you go and see the seawater and collect the seawater, and then just dry, simply dry with room temperature, or you can maybe boil with your range. So you can just evaporate. So what will happen is that first the seawater, if you remove the water evaporation, you will get the calcium carbonate first with the 50 gram per liter concentration, which means the 5% of the seawater will start precipitate calcium carbonate. And this is called very much professional technical name. And when you increase more, like 70 gram per liter, which means 7%, this is the almost you evaporate water 2 times. So 50% of the recovery you have from seawater, you will see calcium carbonate, which is a gypsum. Gypsum is one of the good material to create your construction material, as well as some road dust control, which is one of the very useful sources. Also, you can create the cement, calcium hydroxide. Calcium is the cement raw material, so that you can collect the construction material. So you have a 70 gram per liter calcium sulfate. And then the sodium chloride will precipitate when you have a 10% of the seawater concentration around this 100 gram per liter. And then when you have a seawater concentration salt, 250 gram per liter, which means 25%, so you will collect the magnesium sulfate and potassium chloride, 300 gram per liter, 30% magnesium chloride. So when you just simply evaporate your water from seawater without any addition, so you will get this precipitates. So you can easily collect. So what's the problem? So there is no problem, because the problem will be this is a very slow process. This is very much a natural condition. But when you evaporate using distillation process, even seawater, so you need the anti-scalant, you need to also some of the pH adjustment. So because this is not adjust the pH, the seawater as it is, so that you will get this kind of result. But when you have a process of desalination, even distillation process, SWR process, you need to put some chemical pH adjustment. So your precipitate pattern will change so that you will get different outcome of your precipitate. So we need to also look at more detail how we can first remove this kind of major compound and produce the useful mineral. And this is the crystal precipitation sequence based on the more detail. So you can see how they evaporate water. When you have almost 1% evaporation of the water, so you will get this magnesium chloride, magnesium potassium chloride crystal. So how we can separate the magnesium and potassium? That could be also one of the problem. And when you have sea salt, so some people they remove this one because this is gypsum. So you create a lot of grain. So your gypsum will absorb a lot of moisture. So your table salt will be taking like a granular type of the salt. So which means you cannot utilize this kind of gypsum table salt. So remove this one, and then people make this table salt without gypsum. But some natural table salt, they have included this kind of gypsum material, which is a different quality. So you are using table salt. Also, this table salt is a very different quality, different contents, also different resources from seawater. So we need to also look at carefully how this contains a different mineral for your salt. For example, the magnesium, when you combine with the 300 gram per liter, and they need to separate with the potassium. So how we can separate? So with the different contaminant impurities. So this is the water process water, and just to use sunlight to dry your water. The magnesium has a high concentration, calcium hydroxide replaced with magnesium and calcium, and the magnesium will create with low pH magnesium chloride. So magnesium chloride, so still you have sodium chloride and calcium chloride inside water, but you have a more magnesium chloride, and this material can be used as a electrochemical process. At the anode, to see you create the chlorine, and this chlorine two electrons with also cathode, so you have magnesium metals in your cathode, so that you change your potential of the oxidation, so that you can separate with calcium, sodium, and magnesium, so that you can create this magnesium with the very high purities. So that's the way we are also utilizing this magnesium metal. And bromine. Bromine is also a very interesting material in seawater. Seawater, you have almost 100 milligram per liter of the bromine concentration. So this can be selectively collected from seawater. It's already commercially available. So we just utilize the chlorine oxidation. So bromide concentration in seawater meet together with the chlorine, and they convert it to the chloride ion and change to the bromine gas condition. So bromine can be produced from chlorination. So this bromine can be used as a gas phase, and then you put the sodium sulfate, sulfur oxide addition, and bromine, and this sulfur oxide with water. So you will have a very high concentration of the HBl, and then hydrogen sulfate. So this can be concentrate your bromine in seawater. So if you look at the schematic diagram, this is the one of the commercially available process. Seawater goes to the intake pipeline. Then you just spray your seawater, and then you put your chlorine, and you have a bromine gas condition will comes to the in this phase. So you put the sulfur oxide gas here, and this bromine combined with your sulfur oxide to produce your HBr, so that you come to this bromine rich gas condition. So you can collect your bromine in this absorbent, and so bromide and the steam, and you have water, and the bromine is gas phase, and you have water and gas. The liquid bromine will have a surface changing. The water is on the top, and bromine is higher density. So it's at the bottom you can collect. So you can have a different color as well. It's a brown color bromine as a liquid condition. You can easily collect your bromine concentration, and then you can use the bromine. So where is the bromine? So nowadays a lot of people have an issue for PFAS, the fluorinated fire retardant. So that's everywhere they utilize the PFAS because of the this is the useful fire retardant. So in your construction material, in the paint, in your any kind of the equipment, also a lot of the fire retardant material currently utilize the PFAS or fluorinated very stable molecule, but the bromide is less harmful than the PFAS material. So a lot of people try to change the PFAS to bromide fire retardant. Also, bromide can be used one of our necessary nutrient, and then some of the pharmaceutical compound can be used. So this is the almost $30 billion market every year, bromide concentration. So people collect the bromine in seawater concentration using this kind of technology, and you can have a better idea to improve this process. Also, rubidium. Rubidium is one of the very interesting element. So this is the very high value because 1 kilogram costs $10,000 because it can be used for by precision lasers and medical application for CT scan beam. Also can be used as a GPS necessary material. So rubidium is becoming more and more important, but rubidium rock is not existing. So that's why people look at the seawater source. So most of the lithium or bromine also has bromine rocks, but the problem is rubidium has no such rubidium mining. They are just like a byproduct. When you produce some of the iron materials, rubidium contain maybe less than 2%. So they collect the rubidium, or so they have a very less fraction of the different rock investigation of the production line. So if you try to find the rubidium in the mining, it's very difficult. So that this seawater, the concentration is 0.2 milligram per liter. Also, it can be very much useful for the high value, so that we can consider as the seawater brine mining. So there are still not commercially available for rubidium recovery. So our group, we have also developed some of the material, potassium, cobalt, the hexacyanoferrite, which is called COFC. So this kind of material can be exchanged with the rubidium and potassium, so that you can have a rubidium concentration, and then you can concentrate further from seawater and release the potassium, and you can have a very high concentration of the rubidium. So that's the one of the example people are trying to recover is rubidium selective nanomaterial development together with also GIF compound together with KCOFC has a very strong absorbent behavior. So this is the rubidium within this your materials. So rubidium go inside of this KCFC and then replace. So you have easily replaced with calcium with rubidium, and then you can have a regeneration with a high concentration of potassium. So that we also have developed this material. Also lithium, already you know that the lithium market is growing because of the battery of the lithium. So I don't want to mention about why lithium is more important. So just mention about lithium mining is around 14 million tons. So mostly Chile, China, Argentina, Australia, they have this reserve. And seawater, 0.2 milligram per liter lithium concentration, 230 billion ton, which means the rubidium is 0.2 milligram per liter, which is very similar concentration of lithium. So that 230 billion tons of the lithium and rubidium can be collected from seawater. The challenging is how we can remove the high concentration of sodium, magnesium, calcium, potassium. So that's a lot of researchers currently developing electrochemical process or ion exchange sieving material using lithium manganese oxide, lithium titanium oxide, lithium manganese titanium oxide as an absorbent. So this is also commercially available to concentrate more lithium concentration from salt lake, but not yet seawater, because seawater is less concentration, but salt water lithium concentration is almost 500 milligram per liter, 1,000 milligram per liter, so that people are very much targeting on the salt lake water to collect this lithium concentration using this absorbent. But in the future, yeah, we believe seawater can be possible with brine using electrochemical process. Then we can also look at the different opportunity with the different absorbent, so we can have a good lithium concentration replacement. So this is a lithium, the hydrogen with the this lithium manganese oxide ion sieve. So hydrogen will be replaced with the lithium because of side effect. The sodium, magnesium, potassium concentration too high to penetrate this lattice of molecular structure. Only lithium and hydrogen can be exchanged. So that's how we commercialize this process, can be improved further. This is what people combine with the MOF. MOF has more selectivity with the lithium side. So people look at the lithium side, the GFA, which is very much a similar size of the dehydrated lithium size. So 0.034 nanometer lithium can only pass through this GF4, so that you can have more selective concentration of the lithium. So that's how we growing this lithium capturing using electrochemical process, absorption process, and this is already commercialized. In the future, so Brine can be targeted if we improve the more cost-effective and robust technology. So at the initial stage, I mentioned about your perspective of the brine mining. So what's your opinion based on my presentation? So you can think about if you have any good idea how you can selectively recover useful mineral from seawater. There are existing technology. Also, there is no commercially developed technology. So how you can improve the existing one, how you can develop something new technology to recover targeted iron. So that will be the one of the very future market of the seawater desalination together with the brine mining. So that's the all I have prepared today. So you can send the email if you have any question. I have now it's 4 minutes left, so we can get some Q&A session for next 4 minutes. Do you have any questions?